The assignment Center of Mass and Systems Review is due tonight, so please don't forget that you have that. Today we're going to talk about the work energy theorem and take notes over that. This is the last section of notes in playlist 4, and a lot of what we're going to talk about today is also going to show up in that homework assignment, Center of Mass and Systems Review. But it's just to kind of reinforce it. So again, don't forget you have that. And then we're going to take notes today on, like I said, work energy theorem. So we're going to examine systems and energy conservation or transfer of energy into or out of our system if we have an open system. We're going to define negative and positive work with respect to that energy transfer, and then we're going to apply the work energy theorem to solve those energy problems in terms of those calculations. So work energy theorem. So you're going to use the work energy theorem when you have a change in a system's energy that is caused by work being done on the system. And the work energy theorem simply states that the work done on a system is equal to the change in energy of that system. So obviously, in order for you to have a discussion about a change in energy due to work being done, that means that your system has to have a net external force acting on it, which means we're really going to be focused on those open systems where we have those net external forces that can cause changes in energy of our system. Okay, and so a net external force applied over a distance will cause this energy change. There's the equation right there. Work equals change in energy. And the units that you're going to be using for both work or change in energy, depending on which one you're solving for, will still be the same as they were in the previous notes. Newton meters, which is a joule as well. Those are both acceptable units for work and both acceptable units for energy. The units for both are kilogram meters squared per second squared. That is the same thing as a Newton meter. It is also the same thing as a joule. But again, we're going to see and apply this work energy theorem to open systems where you have a net external force. So if you have a force acting on your system, then you will have a change in energy of your in your system, and you can use the work energy theorem to help you solve for that value. Okay, now if we have an isolated system where we have conservation of energy and momentum and mass, then your mechanical energy is going to be conserved, and there is not going to be a net external force on your system because you will have internalized all those forces in the way you defined it, and you won't be able to use the work energy theorem in a scenario where you have an isolated system. You have to define your system in such a way that it can exchange energy with its surroundings in order for you to be able to use that concept of the work being done is equal to the change in energy. Obviously, if there is no change in energy, there is no work being done either. Okay, so again, work is energy change. We talked about this when we talked about work. We talked about it on the previous slides. But if you have an increase in the energy of your system, that means that you have positive work being done on the system. Okay, so again, if you have a situation where you push something and you cause it to speed up, then that's going to be an example of positive work because you're applying a force for a certain distance and you have increased the energy of that system. On the other hand, if your system loses energy, that's going to be negative work because, as the work energy theorem has stated, the work done is equal to the energy change. So that change in energy could be positive if you're adding it, but it could also be negative if the work being done is removing energy from the system. So you need to remember that work can be positive or negative depending on whatever the scenario is that you're looking at, and the way that you're going to determine that beyond just looking at the angle at which the force is applied. The other thing you can ask yourself is this force adding energy to the system, or is this force removing energy from the system? So let's talk about these bar charts again, because this was the way that we talked about visualizing energy previously. So now we're going to go back to these bar charts, and we're also going to look at what that's going to look like when you don't have conservation of energy. So when you do have a system where you can have a change in your energy because it can be removed and go out to the surroundings, or you can add in energy to your system. So for this particular bar chart here, obviously I know that this is not an isolated system. This is probably going to be an open system. If my initial mechanical energy is not equal to my final mechanical energy, then I know that I have a situation where work is being done to cause a change in energy. So in this case, with this example, is the work being done positive work or is this negative work? Negative, because I have less energy than I started with, which would imply that it was removed from the system. To indicate that the work is negative, you're going to use this middle section and you're going to place the block down here below this kind of zero line, if you will. And this states that you have negative work being done on the system. And the reason we want to be able to visualize this is it helps us to write our equation. Ultimately, you have to be able to write a formula from this. Okay, so whatever you have over here for your initial state, whatever energy forms are present, you'll have a sum of those initial bars plus any work done by an external force, and you're going to set it equal to the sum of any of these final bars over here. Okay, and that's how you're going to write the equation. Now this is just an example, so let's look at some with some context to it. We looked at this example in our notes previously. It says a clay blob is released from rest and it falls until it compresses a spring and comes to rest. And this is the same slide we looked at previously. I have a bar chart drawn here, an energy bar chart for my clay spring earth system. And whenever I define my system as the clay spring earth system, I should have conservation of energy because I have included both the spring, which means I can say that that gives me spring potential energy, and the earth, so I can say that I have gravitational potential energy because I've included those in my system. And so you'll see here that the total initial amount of gravitational potential energy will equal the final amount of gravitational potential energy. Since it's on a spring, it's not on the ground, there's still some height, plus whatever amount of elastic potential energy is now stored in the spring. Okay, so we can have conservation of energy if we define our system that way, but is there a way for us to define this same scenario, to redefine the system so that energy is not conserved? Any ideas of what we could do? Clay spring, sure, that would do it. Clay earth, sure, that would do it. Just the clay. Anything where you have one of these forces as an external force acting on your system. I'm going to start with setting it up as the clay earth system. Okay, again, all those answers were good. Okay, but I'm going to start with this one, clay earth system. If I call it the clay earth system, only the force of gravity is internalized, which means that spring, not in my system anymore. So I don't have elastic potential energy anymore whenever I draw my bar charts. Instead, I have an external force from the spring that can do work on my system. And that's going to show up in my bar chart. Because I still start out with gravitational potential energy. I'm still above the earth's still part of my system. But when that clay falls, it does end up lower, but now we don't have a spring in the system, so we can't include that elastic potential energy. Instead, that same force gives us work done on that system to remove some of that initial energy. So we have our equation that looks like this, our gravitational potential energy initially plus the work done by the spring equals our gravitational potential energy at the end. Okay, and so we're still accounting for all of the joules, okay, because again we have energy and we have our energy change for our work. We're still accounting for everything, but now we're including work because of the way we defined our system. Are there questions about this one? Okay, one of the other suggestions I heard was this, clay spring. Okay, well guess what? If it's a clay spring system, whenever I release this clay blob from rest, if I'm just holding it off of the ground, does it have energy? No. Okay, if you're just holding it up above the ground, you can't say that you have gravitational potential energy unless the earth is in your system, because gravitational potential energy is your position relative to the earth, and if that's not part of your system, well, you can't account for that form of energy. So you wouldn't have any energy at all initially, but you would at the end have a compressed spring, which is part of your system, so you would have that energy at the end, but no gravitational potential energy at the end because, again, there's no earth in the system. So where does that spring energy come from? Well, it comes from the work that is done by the clay when it compresses that spring. So that external force of gravity that's pulling down on the clay allows that clay to compress the spring, and that gravity does work on the system. Yes?
So initial energy of the system plus the work done on the system will always equal the final energy of the system?
Yes. Yeah, and if there is no work, there's no work to add in that equation. Okay, so here is what my equation looks like. I don't have any initial energy to add, so it's just the work done by the force of gravity in pulling that clay down. And that work that's done by the force of gravity will give me the elastic potential energy that's in the spring once it's been compressed. And I can set them equal to each other. Okay, so again, depending on what you need to solve for, you have to define your system appropriately so you can find it. If I ask you, for what the work done by gravity is, then you're going to want to define it this way, because now you can see that there's work done by gravity. You wouldn't want to include the Earth in your system. If I wanted to ask you about finding the work done by the spring, same idea. You wouldn't want to include the spring in the system. You need to consider what you're solving for in any given problem. Okay, now, whenever we talk about these systems where we have external forces acting on the system, obviously you're going to have a change in energy. That's the whole point. That work causes an energy change. And so oftentimes you'll see questions where you're going to be asked to calculate the mechanical energy loss. Because a lot of times it's just asking about something going over a frictional surface or air resistance or something that's going to cause energy to be dissipated from the system. And so if you have a question where it's asking you to use the work energy theorem to calculate the mechanical energy loss for the system, there's an equation up on my screen that allows you to calculate the percentage of the mechanical energy that's being lost. And you do need to write this equation down because it is not on your formula chart. However, it's the same basic rule for finding a percentage every time. It's always part divided by total. The total amount of mechanical energy would be the amount you started with. If you're losing energy, obviously, the total is what you start with. And then you have your change in energy, how much you lost, which is also work. Okay, and so that's the part lost divided by the total times 100. That's going to give you your percentage of energy loss. You can write it this way. Percent loss is change in mechanical energy over initial mechanical energy times 100, or recognizing that change in mechanical energy is work, you could write it this way. Work over initial mechanical energy times 100 should give you the exact same answer depending on which way you are thinking about the problem. But you do need to be able to solve for percentage of energy loss. Don't mix it up. If I ask you for the percent remaining, obviously you'd give me the other part of that. Okay, so let's try an example calculation. Okay, so we're going to start with the bar chart so that we can visualize everything and then get our equation from there. And once we have our equation, then we can actually work on solving it. So this question says a 0.3 kilogram cart travels 3 meters per second on an elevated track and then rolls down a 5 meter high incline to the ground. There, the cart travels across a rough surface for 3 meters, causing it to have a final speed of 1.2 meters per second. Find the force of friction for the rough surface. Guys, if I want to solve for force of friction, I need force of friction to be an external force. I need to define my system in such a way that friction acts on the system as an external force and does work on the system, because I can figure out what that work is by figuring out my energy change from the information I've been given. So when we set up our system, we're going to call it the cart-earth system, so that the only force acting externally is the force of friction. The Earth's got to be in there. I need my gravitational force internalized because I just want work done by friction. Okay, so now if we think about the forms of energy present with our cart-earth system, our cart is initially moving 3 meters per second, so that's going to be kinetic energy. The cart is also on an elevated track that's 5 meters high, which means it has gravitational potential energy. There is no mention of a spring or anything elastic, so this is my total initial energy is kinetic plus gravitational potential energy. At the end of this scenario, it says that the cart is still moving. It's on the ground because it says to the ground right here, and it's still moving 1.2 meters per second, meaning it still has some kinetic energy, but it has lost that gravitational potential energy that it started with. And I know that I have a loss here of energy. If I look at my initial and final, clearly I lost some. I lost 3 blocks, whatever that represents. And so I know that there's negative work being done on the system, which makes sense because it tells me there's friction. Friction always does negative work. Okay, and so this is how you would visualize it, and then from this you write your equation. So the bar chart's really more helpful to get you started with the equation. If you can write the equation without a bar chart, then fine, you don't have to have a bar chart. Okay, but you should be able to interpret a bar chart if you're given one. So my equation looks like this: my initial kinetic energy plus my initial gravitational potential energy plus the external, the work done by the external force of friction equals my final kinetic energy. So if we take this equation and we want to solve with it, I need to put some variables in here. My question doesn't give me any information about energy. It gives me masses, velocities, heights. So let's put those variables in instead. Kinetic energy is 1/2 mv squared. So my initial kinetic energy is 1/2 mv naught squared. Gravitational potential energy is mg delta y. So I have mg delta y naught plus work is FD cosine theta. So that's going to be my work done by friction. And then it's all equal to that kinetic energy at the end, 1/2 mv squared. So again, we're trying to solve for force of friction. I'm looking for this single variable right here, this F. If I plug in, if I know that this F is force of friction and I plug in my angle. Anybody know why I used 180 degrees for my angle for friction? Friction always opposes the motion of the object. If you have something sliding across your desk to the right, friction's to the left. And it's parallel to the surface. So it will be at 180 degrees to the direction that the object's moving, always. Guys, what's the cosine of 180? -1. So I could just do this. Negative force of friction times the displacement. Because all I'm doing is FD times -1. So there it is. All right, from here, we want to go ahead and isolate this variable because we're trying to solve for force of friction. So I'm going to subtract these to the other side, leaving me with this. Negative force of friction times my distance equals 1/2 mv squared minus 1/2 mv naught squared minus mg delta y naught. Okay, and so all I did was move these over here to the other side. I do want to get rid of this negative sign because I'm ultimately trying to solve for force of friction. So I'm just going to multiply the whole thing through by a negative, and that leaves me with this. Force of friction times distance equals negative 1/2 mv squared plus 1/2 mv naught squared plus mg delta y naught. From here, I just need to divide both sides by that distance, and now I can substitute in. So now you're going to plug your numbers in. When you plug them in from the question, you get this. Okay, yes, it looks lengthy, but it's not super difficult math. As long as you type that correctly in the calculator, you should be good. When you enter this, you get a force of friction of 5.378 newtons. So again, this is using the idea of conservation of energy, but in a situation where the energy is actually not conserved due to work being done. So you can use the work energy theorem along with those conservation concepts you've already learned to solve a problem just like this one. Are there any questions about this particular problem? All right, that's the only example one that I have for you in today's notes. In fact, that's the end of the notes. So for the rest of the class period today, you could work on playlist 4, which is due next week, or more pressing would be the Center of Mass and Systems Review homework, which is due tonight. Reminder, lab feedback for your work and power lab is due Monday. The lab itself is due on Wednesday. And then roller coaster next week is the actual build, okay, at the end of next week. But next Tuesday is another roller coaster Q&A day. And if you want to bring in some belongings to actually try to build something and test it out, you could do that on Tuesday. But that means that you need to have a discussion with your group about who's going to bring what. If you want to bring in tape to help you attach it to the wall, you have to bring your own tape. If you want toothpicks to attach it to itself or a paper clip or whatever you plan to use, bring it in. Okay, I will say, and it says this on your sheet, we don't want duct tape because it removes paint from the wall. Okay, now if you use duct tape to connect your track to itself, I don't really care. But you don't attach it to the wall with it, it will actually peel the paint off of the cinder block. So again, talk to your group about whatever materials. If you don't already have insulation tubing, you don't have to worry about that. We have some here you can use. Okay, if you have your own, you're welcome to bring it in. But you can't take ours home. So if you're wanting to practice stuff over the weekend, you need to get your own. Edits to preliminary data are also due Tuesday, so if you're doing a redesign because your first one didn't work out so well, then that is also something that needs to be on your radar. All right, I'm gonna let you guys get to work. If you have questions for me, please let me know.